Okay, so basically I want to look at how many zeros are there for a polynomial of degree n. Okay, we expect that the number of zeros cannot exceed n. We should not expect that it will always have n zeros, because we know even in R that this is not true. Example, x square plus 1 has no zeros over R, right? X square plus 1 has no zeros in R, right? So we know that we should not expect that it will have n zeros, but we should expect that it will have at most n zeros, and that's what we are going to prove. Okay, so to do this, because the intention will be to go by induction, okay, the intention will be to go by induction, so we'll have to prove a small lemma to this theorem first. So that is, so let me ask you what you expect, and then let's prove it. So let f of x be a polynomial in fx. Again, I'm not writing here, f is a field, okay, and alpha belonging to f be 0 of fx of degree, let's see, so the degree of the 0 is n. If we can write, so we know that we can write, if f of x is equal to some, we know we can do this, x minus alpha raised to n times p of x, right, where of course p is in fx. Okay, again, since this is a 0 of degree n, p of alpha will be non-zero, right, because if p of alpha is 0, then x minus alpha divides p, and then you can combine this with this, and that will tell you that x minus alpha raised to n plus 1 divides f of x. So that's not possible. So therefore we know that p of alpha is non-zero. So if f of x is equal to x minus alpha raised to n times p of x, I want to talk about the roots of f. How can I relate the roots of f and the roots of p? Okay, so if let's say let for some, okay, so if beta is a root, or if beta is some element in f where beta is not equal to alpha, okay, then beta is a root of f of x of multiplicity m if and only if, if and only if. So what do you expect? How can I relate this to be a root, as a root of p of x? Yeah, so one, definitely if beta is a root of f of x, it will have to be a root of p of x. Why? You use the evaluation homomorphism on both sides, you will get f of beta here, which is 0, right, because it's a root of f of x, and here you will get beta minus alpha raised to n. Since beta is not equal to alpha, this will be non-zero, so therefore that has to be 0. So it has to be a root of p of x, but of what multiplicity? It has to be, we should show that it is of the same multiplicity m. Okay, if and only if beta is a root, and you also need to show the other side, okay, that is, here if beta is a root of p of x, then obviously it's a root of f of x, because this side will come 0, right. So this will be 0, f of beta will be 0, but you need to show it's of the same multiplicity. Okay, so if and only if beta is a root of p of x of multiplicity. So once I do this, what will it tell me? Okay, so the idea again, the reason I am doing this is I want to prove that a polynomial of degree n has at most n roots. Okay, so how will this help me? Because what will the roots of f be? The roots of f will then be alpha of multiplicity n and the roots of p of whatever the same multiplicities, exactly the same. Now the degree of p, so if you look at the set of all roots, right, it will be alpha and the set of all roots of this with the corresponding multiplicities. But look at the degree of p. The degree of p is lesser than the degree of f, right? Because the degree of f is n plus the degree of p. So the degree of p is the degree of f minus n. So I can go down, right? So then I can use the induction hypothesis on f, on p, and I can get my result. That's the basic idea of the induction. So if I prove this, then that is almost done. So let's try to prove this result. So let us see here. I'm going to use the previous corollary itself. So suppose beta is a root of, suppose beta is a root of f of x of multiplicity m. So what does this mean? It means that there exists some there exists some g of x in fx such that I can write f of x, because this is a root of multiplicity m, right? So I can write this as x minus alpha raised to m times g of x, and g of alpha is non-zero. That's what we have discussed. Okay. Now the intention is beta. Okay. Now the intention is I need to write p of x. I think I need to do the other side first. I'm sorry, I need to go with the other side first. I'll tell you why later. So suppose beta is a root of p of x. We will see why it is required to do this. So I can write, this is very easy to see. So p of x in this way. Okay. Now what can we do? See, what's the intention? Write f of x as x minus beta raised to m times some polynomial such that beta is not a root of that polynomial. Okay. So I can substitute this in place of p of x, right, to give me f of x is equal to, just substitute this here. What do you get? I can write this as x minus beta raised to m times x minus alpha raised to n times g of x. Is this okay? Is this okay? If I substitute this up here, this is what I get. Okay? Okay. Now I can take this as some g1 of x, right? I can write this as some g1 of x, where g1 of x is x minus alpha raised to n times g of x. Okay. Now I have got f of x as x minus beta raised to m times g1 of x. What is left to do to prove that beta is a root of multiplicity m of f of x? What do I need to show? Yeah? Yes? I have written f of x. When is alpha a root of f of x of multiplicity m? Yes, the other corollary, the equivalence statement. If I can write f of x as x minus alpha raised to m times g of x such that, exactly, such that g of alpha is non-zero. So what is left to show here? g1 of beta is non-zero. Okay, I need to show that g1 of beta is non-zero. Can everyone see why g1 of beta is non-zero? Yes? What happens to G1 of beta? We know that because the evaluation map is a homomorphism, right? So G1 of beta will be evaluate beta in this place into evaluate beta in this place. So that will give us beta minus alpha raised to n times G of beta. Okay, these are both elements of the field. Beta is not equal to alpha, so this is non-zero, right? And we know that G of, this is not G of alpha, this is G of beta. It was a mistake. Okay, so we know that this is non-zero and this is non-zero. Fields cannot have zero divisors, so this is non-zero. Okay, so therefore, beta is a root of f of x of multiplicity m. Okay, now let's prove the converse. Suppose, so I'm going to use a small trick here. Okay, so conversely, suppose beta is a root of f of x of multiplicity m. Okay, so suppose beta is a root of f of x of multiplicity m. What will this mean? This means that f of beta is 0, right? F of beta is 0. That's because we can see that this thing, right? Because f of x can be written as some x minus beta raised to m times p of x. You substitute beta in that place, you're going to get 0. Okay, so therefore this will happen, which will mean that, so f of beta here is nothing but beta minus alpha raised to n times p of beta. This is 0, right? But this cannot be 0 because beta is not equal to alpha, hence this has to be 0. Okay, so this means that p of beta is 0. Sorry. What does this tell me? It tells me that beta is a root of p of x. Okay, so this means that beta is a root of p of x. So the multiplicity of this should be at least 1. The multiplicity of beta is a root of p of x will be at least 1. Okay, so let's say that the multiplicity is k. What will that mean? So suppose beta is a root of p of x of multiplicity. So I know it is a root. I am saying that the multiplicity is k, multiplicity k. Okay, now by the previous statement, what does this tell you? What we have proved earlier. If beta is a root of p of x of multiplicity m, then beta should be a root of f of x of multiplicity m, right? So this will tell us that beta is a root of, by the previous argument. Okay, you can go down in exactly the same manner and you will see that beta is a root of p of x of f of x of multiplicity m, sorry, of multiplicity k. Okay, but we know that beta is a root of f of x of multiplicity m, right? That means x minus alpha raised to x minus beta raised to m, right? The highest power that you can divide this by, the highest power of x minus beta that you can divide this is m. Here the highest power that you can divide is k. These two have to be the same. Okay, so therefore k has to be equal to m, and we proved our result. Okay, because k is what? K is the multiplicity of the root of p of x as a root of p of x. So that gives you your result. So this essentially tells us that other than the roots of alpha, other than alpha, the roots of f of x and the roots of p of x are exactly the same, even considering the multiplicities. Okay, taking into consideration the multiplicities, the roots of f and the roots of p are exactly the same. Okay, and this is sufficient to then prove the interesting result. Okay. So I hope you understand why we have done this. The reason for this is so that now I can use induction. I think that most of you need to go through this converse again. The converse, the argument in the converse is a little tricky because I'm actually using the previous argument in the converse. Okay, so you would need to go over the argument again, try to write it on your own and see whether you have got the idea. Okay, so the next theorem tells us that if f of x in fx is of degree n, even then f of x has at most n zeros. Okay. By the statement itself, since we are talking about the degree, f of x cannot be the zero polynomial. The zero polynomial is the only polynomial which has a zero at every point, right? That's the odd one. That's some of the reasons why you don't want to put a degree to it, right? If you give the degree to be 0, then it does not follow this statement because the 0 would be this thing anyway. So that's so. Let's prove this when n is 0 first. Okay, when n is 0, what happens to the function? It's a constant function, right? How many zeros does a constant function, non-zero constant function, right? If we want to be more specific, how many zeros does the constant function have? Nothing, right? Constant function cannot have any zeros, right? Constant, not function, constant polynomial. I should be clear about that. Okay, so if n equals 0, then f of x is a constant polynomial, hence f of alpha is not equal to 0 for every alpha in f. Okay. And therefore f of x has no zeros, because f of alpha will always be that constant value, non-zero constant value. So that is non-zero, right? It's a non-zero constant polynomial. Okay, f of x has no zeros. So it satisfies the criteria, right? It has at most 0 zeros, right? So it satisfies the criteria. Okay. Let's also do it for 1. Okay, let's do it for 1. Let's see who can you actually don't need to do it for 1 because this is sufficient, but let's also do it for 1. Okay, so if n equals 1, that means the degree of f is 1. Let us say that we can take f to be, okay, I will start writing it in this manner, that is not writing it in the series form. I will start writing polynomials because I understand that you know that they are actually formal power series, but give it a easier notation. So let's say this is ax plus b, that means the coefficient of x is a and the constant coefficient is b and everything else is 0. Okay, so in this case, can you tell me whether this has any zeros? Yeah, minus b, 1 0. Which one? Which is the 0? Minus b. minus b times A inverse. Okay, so this can have only one 0. How do we know that? Because say suppose alpha is the 0, if alpha is a 0 of this, okay, obviously we know that what is it, minus b times A inverse is a 0 of this, right? Because if you substitute that here, put at minus b times A inverse, if you substitute that here, you will get you see the A and A inverse will cancel and you will get minus b plus b, which is 0. Okay, now if alpha is a 0, you need to show it is that there is no other 0. Okay, so if alpha is a 0, what happens? A alpha plus b is 0, right? Now you can take your b to that side, add by the additive inverse of b on both sides, you get A alpha equals minus b, and then multiplying by the inverse of A on both sides, you get alpha has to be minus b. So alpha is a root of f of x, right, if and only if A alpha plus b is equal to 0, which happens if and only if alpha is equal to, I am just ignoring the calculations, minus b times A inverse. So this tells us that there is only one root. Okay, so therefore f of x has exactly one root, 1 0. Now let us assume the case when, let us assume that the statement is true for all polynomials of degree less than n. Okay, for all polynomials we are going to use strong induction. Yeah, that's the one. Yeah, so f of x has exactly 1 0, of multiplicity is also 1, of multiplicity. How do I know that the multiplicity of this is 1? How do I know the multiplicity of this is 1? So you have to write f of x. Can anyone tell me? You need to write f of x as x minus so x minus b by a, so plus b A inverse times g of x, where g of minus b times A inverse is non-zero. How will you do that? What is this g of x? Check properly. Yeah. It is a, I suppose. No? A, right, that's right. It's a constant polynomial a. Right. That's the constant polynomial a. Right, that works. So this tells you that the has exactly 1 0, of multiplicity is, the multiplicity of this is also 1. Okay. Let me simply write here as f of x can be written as a times alpha plus b A inverse. Okay, so let's make the induction hypothesis. Yeah, so f of x is of degree n, then has at most zeros. Counting multiplicities is the way we write. Counting multiplicity. How do we? What do we mean by counting multiplicities? For every 0, you count the number of multiplicity that is associated with the 0. Okay, so what would be just, so counting multiplicity is how many zeros this would have? 3. Counting multiplicity, because 2 is of multiplicity 2 and 3 is of multiplicity 1. So counting multiplicity, it will have 3 zeros. The multiplicity associated with 2 is 2. The multiplicity associated with 3 is 1. So 3. Okay, so that's something. Yes. So assume the statement for any polynomial in f of x, or for any, let's say, non-zero of degree strictly less than n. Okay, and now we want to prove this for a polynomial of degree m. Okay, so let f of x be a polynomial of degree n in fx. So there are obviously two cases. One is f of x has no zeros. If f of x has no zeros, is there anything to prove? No, because then it has zero this thing, so it obviously satisfies the statement. Okay, what if f of x has a zero? So if f of x has no zeros, there is nothing to prove. There is nothing to prove. So we assume that f of x has a 0 alpha. Okay, we'll take 1 0 to be alpha. Okay, and we'll let m be its multiplicity. Let m be the multiplicity of alpha as a 0 of f of x. What will this mean? This means that you can find some g of x in fx such that f of x can be written as x minus alpha raised to m times g of x, and g of alpha is non-zero. Now, by the previous exercise, what do we know? By the previous exercise, okay, so by the previous exercise we know that the zeros of f are essentially alpha of multiplicity m and the zeros of g of x of the corresponding multiplicities, right? So by okay, what happens to the degree of g of x? What will the degree of g of x be? We are working in a field, so what will be the degree of g of x? N minus m, because the degree of f is n, so the degree of this will be equal to the degree of this plus the degree of this, right? So the degree of f of x, which is n, okay, will be equal to m plus the degree of g of x, which means that the degree of g of x is n minus m, which is strictly less than n. Okay, so therefore by the induction hypothesis, okay, g of x has at most how many zeros this will have? By the induction hypothesis, the number of zeros of this will be, has at most, let's call this as k, not use k anyway, right? K equals degree of g of x, zeros, counting multiplicities. Okay, so counting the multiplicities, this will have at most k zeros. This is by the induction hypothesis, because we have assumed the statement for any polynomial of degree less than n. g of x is a polynomial of degree less than n. Yeah, this is n minus m, no? I am just setting k to be the degree so that I can use k instead of writing degree of g of x, okay? So, now by the previous theorem, so by the previous exercise, because the degrees, the zeros of f are essentially alpha of multiplicity m and the degrees of g of x, right? So, by the previous exercise, f of x has at most how many zeros? At most m, that is the multiplicity of alpha, right, plus k, the number of zeros of not k, yeah, k. It has at most this many. This one has at most its degree number of zeros, right? By the previous theorem, the zeros of this is going to be m plus the zeros of this, but this upper limit is k, so therefore the upper limit of this will be m plus k, right? So this is m plus, or we can simply write degree of g of x, okay? So this has at most this thing which is exactly n. That proves our theorem. I think we'll stop this here.